Everyone, this is Ross Blocher. He is uh, a animation trainer at Disney.
Mhm.
He's worked on in a technical capacity on such films as Frozen 2, I think like the Simpsons movie, and some other things. He's also a co-host of the podcast Oh No, Ross and Carrie.
Thanks for having
So,
me. Good to talk to
yeah,
you.
thanks for being on the program. So let's get started. So, what is your background in animation, and what is your job at Disney? I mean, animation
Yeah,
trainer.
I'll try to give you the relatively quick version of this, but I studied animation at Woodbury University. And shortly after I graduated, I found that kind of the roles I always fell into were related to compositing or technical direction. So that's taking all of the different pieces and kind of putting them together, layering them. And it involves a lot of fun collaboration with other artists and oftentimes many creative aspects itself. And my first kind of big break, or at least first film, was the Simpsons movie. So worked on that, and then I knew a lot of the people that were going over to Disney to work on Princess and the Frog, and I had to work on that. I just had to. And so I hit up all of my connections and did everything I could to get over there, and succeeded.
So let's see. Next question here, which is very related. How does the math in animation serve the creativity and vice versa?
Yeah, that's a really interesting question, and I might even broaden math to technology generally, but um, it's always a back and forth where the directors, the storytellers will come with these new ideas, and they'll say, "Can we do this?" And almost with every production, then the artists and the technical professionals, they'll all kind of look at this and go, I think so. We've never done anything quite like that before, but we want that because if we kept making the same film over and over, that would be very easy to do. But then you wouldn't be pushing yourself. You wouldn't be learning anything. So there's always that element, of someone coming in and saying, "Hey, we're going to make this character that's made out of 50,000 smaller versions of that same character. Can we do that?" Then we figure out how to do it. I don't know. Have you seen Ralph Breaks the Internet?
Oh, not yet. I've seen the first Ralph one. I need to see the second one.
Okay. So you'll
So
see.
bad at getting around to actually seeing the new movies, especially now that I live by myself in Canada.
But
But
it'll play in reverse too, though, where we'll say, okay, we have this new technology, and for example, we've moved towards ray tracing in our rendering process, like where we create the final imagery and simulate essentially the real world inside the digital one, and that's a more realistic representation where it's simulating the real world. It's plausible lighting. So now the artist can kind of go in and they can say, okay, so I'm in the setting and I've defined where the sun is or what time of day it is, and I have a lot of this in place. Now I can kind of tweak and adjust and optimize. Whereas before we got to the place where ray tracing or global illumination itself as a rendering procedure it was computationally too difficult. It would have taken too long, too many machines, just would have been impractical. So once we got to that place, and there was a whole lot of linear algebra that paved the way there, once we got to that point, then the artists had a lot provided to them. But before that, they had to really kind of cheat a lot and do a lot more work to get you to that point.
now, to get to linear algebra specifically, so you've already given one example of how linear algebra is used in animation. Are there any others that you want to discuss?
Oh yeah, well, I mean, pretty much at every stage of animation in the CG world, every level involves linear algebra on some end. Now it's mostly handled on the back end. The computer's doing a ton of linear algebra at every moment because it's moving points in 3D space, so it's calculating vectors. And for example, I mentioned like texturing. So once I've created a 3D shape and I've animated it, I can also add textures to it. So I'm just going to keep using parts of my body because that's the thing I have handy here. Maybe I'll use my mouse or something. But if I have this object, I can then say, I have this blue paint applied to it. Now, originally that blue paint is going to be a 2D object that is then applied here. And I could render this out with its motion, but then I could say later on, you know, like, well, make it pink. And then I could go in and I could just modify that 2D illustration from blue to pink. And now it's automatically, changed, and now it's appearing on the 3D object. And that's, you know, that's a subspace. Essentially, you have this 2D plane that is a subspace of this 3D object. And so we have a bunch of calculations that are going on in the background, and in using, you know, matrices to transform these points from one space to another. We were also talking about rendering. And so when you're doing that, you know, the way that we're handling render, like for every frame, we talked about 24 frames per second. For every frame, there's over 2 million pixels in a 2K image, you know, 1920 by 1080 or whatever resolution it is you're using for your film. And so essentially what you're doing is from each pixel location on the screen of all these pixels, you're emitting rays into the world and seeing where they bounce off of other objects. And so I'm bouncing off of, you know, the object I'm seeing. Let's say it's a ball, you know, that's sitting in front of me. And then I need to figure out, okay, well, when I bounce off of that, I need to pick up information about its local color space. So I'm making a query on that object. I need to figure out at that exact geometric point on the surface, what color data am I picking up from that object along with any other information.
What do you mean by color data? Do you mean like what the color is of that object at that point?
Yeah, that texture, you know, whatever's been painted onto it. And, you know, there may be additional layers where we're doing subsurface scattering, and we're, you know, we're picking up a specular light. You know, there may be like 3 different lighting passes, but ignoring that complexity, you know, then I also need to figure out, okay, well, what's the normal of that surface? And so I know exactly where to rotate out into, or reflect out into 3-dimensional space, so I can search for my next point. And maybe I never run into anything, and that ray goes off nowhere, and then I can optimize my equations to say, okay, well, we don't need to calculate for that anymore. We can ignore that ray. It's it's essentially disappeared into space, you know. But then I can look at those other rays, and there's going to be millions of them. So for any given frame, there's going to be hundreds of millions, even billions of those linear algebra calculations that are happening as I'm tracking these vectors.
Does it, so let's focus on one of those examples. Choose whichever one you'd like. Choose one. Choose one.
Okay, let's see here. I'm trying to think of one I could speak to the best. Let's talk about, you know, actually, let's talk about doing simulations.
Okay, so why is this example important, extremely important to animation?
So when it comes to, like, let's say simulating, goodness, there's so many things we simulate. So effects animation is animating anything that's not a character. And so you might have to, within a film, you're going to need to have a character interacting with, say, well, water, you know, and maybe there's a film where the water is kind of like a character in and of itself and has a personality and it responds to certain ways. You know, it's important to animation because you can breathe life into that in a way that has something feel physically real, but it's doing something that you never see in reality. And that's the magic of animation, is all of a sudden, you know, you're bringing to life, you're animating, well, I mean, that's the term, right? Animation is bringing things to life. It's creating motion. So you're bringing to life something that maybe held kind of a background role in someone's mind or wasn't a sentient agent. And then, you know, linear algebra is helping you then do that efficiently. So if I'm trying to simulate a wave, I may first work kind of on an algorithmic level to create a simulator that can generate waves, and then, you know, make them look realistic and have them interact with that ray tracing that I was talking about to render them out so they look and feel like waves. But now I need to give tools to the artist so that they can manipulate that and animate it and have it do things that will then, you know, end up on screen as something new and exciting and magical.
Why why, you've kind of already talked about this, but why is linear algebra necessary in this example?
Yeah, well, again, anything you're doing inside of the CG space is just constant linear algebra going on in the background, just to translate those points that are creating the outlines of the shapes, essentially, but also so much data that happens within that. And a simulation, in particular, is incredibly difficult because you're often performing these calculations on a level that is so deep and detailed that you're trying to simulate reality. And the better that you can do that, to kind of like simulate things on a molecular level, the more realistic the end result will look. And so I was talking to one of my friends who's a software developer, David Adler, who's fantastically helpful surrounding some of my examples with their mathematical correlates. But you can, like, if you're, say, if you're calculating this motion of these waves, let's say, you have set all of these points and you've got thousands of points and you're representing this data and their location by matrices that can get up to, like 1,000 by 1,000 tables, like insanely complicated stuff. And so what, you can do with an operation in the background is kind of give yourself at least a domain of definition. So you can say, okay, well, I have a fair sense of the probability of where any of these points is going to be located. And by using that, I can then avoid calculating extraneous details. So I can essentially set a bound upon all of those calculations. Okay, all of my probable values are within here. Let's do the calculations here. And then I'm lining up a bunch of columns and rows of values that are essentially zero or close enough to it, from my perspective, that I can remove those from the calculation altogether and make all of this happen faster, faster.
Okay. Let's see. So let's see. The last question here is, which linear algebra concepts are used in this example? So let me see if I can try and do a little bit of a guess so far. Of course, you have matrices where you're going to be transforming vectors in space. You're going to, like, if you do a simulation, you're going to need to have transformation telling you what happens at every point and everywhere from this time period, this frame to the next frame.
Right, because time is another dimension in all of it.
Yeah. And then if you're going to try and move things within, you need to know how things are going to be moving. And would you be doing, I guess, would there be much with subspaces or any of the other kind of topics here?
In simulation, I mean, probably not that I could speak to in this particular example.
I was thinking the subspaces would be more with that, the textures that you have, like what your example with the mouse.
Mm-hmm. Yeah, and I can't speak to this in any depth, but I think even there you could, in simulations, you could probably use eigenvalues to kind of help at least define, sort of take all of that massive amount of data and organize it in such a way that you kind of define like the primary calculations that you need essentially to manage that data. That could save you a lot of time.
Yeah. That's one of the big benefits of people actually using the eigenvalues and eigenvectors is to kind of, like, once you have all those, you can now save time with the calculations of all your matrix and everything. So diagonalization, which might or might not have been talked about by the time this video is posted. So I'm not entirely sure. I haven't decided when to post this yet. But so that's all I have on my list. Thank you for being this interviewee.
My pleasure, and hopefully I've helped communicate a little bit of the value of mathematics in the arts, but also animation in particular, and maybe it's something now you're thinking about in the future that you know, you could apply your skills to, because we need them.